Good afternoon. We're having a review session, and it's very difficult for me to do a review session because you probably think what he's talking about will be in the final. In the final, anything can be that we have discussed here that was part of your homework, and this was part of your reading assignment, okay? The final will have 60 questions. Each question is 4 points. We will have 3 hours for that. It's on Wednesday from 8 to 11, and that's the 9th of April, and I understand it in 100 Haas auditorium, 100 Haas, but you will get a notification about this from through B-Space. Okay, you'll all be sitting in the same room. Okay, I also will be there. Okay, so the last time we have talked about all kinds of things. We have talked about nuclear chemistry, and you have a nuclear chemist already because you know the different decays, and you know what a half-life is, and you know what the exponential decay law is. And we have talked then in lecture 38 about the redox reaction, and you know redox reaction, the name redox has reduction and oxidation. They must have 2 partners, one that furnishes the electrons, and the other one that takes the electrons. The one furnishing the electrons is being oxidized, so its oxidation number, you need to know what an oxidation number is, increases due to the loss of electrons, and is called the reducer, okay? That's the one that has the lower potential compared to the oxidizer. The one that accepts the electrons is itself being reduced. That means the oxidation number decreases due to the gain of the electrons, and we call this the oxidizer. So the oxidizer is picking up these electrons, and they come from the reducer, and the oxidizer is the one with the higher electrochemical potential, and it doesn't have to be necessarily positive. If it's higher than the one below, the one which is going to be which is going to be oxidized, the reducer is going to be oxidized, then you have an electrochemical cell, or you have a redox potential. And so galvanic cells are made of 2 electrochemical half cells. This one would be a half cell, the one is the reducer is a half cell itself, and then the oxidizer is a half cell. And we know the reduction occurs on the cathode. This is the right side of your diagram. This is the international convention, even if your GSIs or the head GSI have told you differently. I insist on that the red cat, the reduction is the cathode, and it's always on the right side. If you write a half potential, the left half potential, double binding the bridge, then double slash the bridge, and then you have the right side, and the right side is always the reduction written. This is how international agreements are doing this. Is the IU Pact. So you know that the loss of LEO goes GER, the loss of electrons is oxidation, and gain of electrons is reduction. Okay, and then you also have oil rig. What is oil? Oxidation is loss, and what is rig? Reduction is gain of electrons. So we have talked about these reactions here, and you have seen that we have copper and zinc, copper ions and copper metal, and zinc metal and zinc ions. And with this we have one half reaction is the oxidation. That's the zinc. The zinc metal goes in solution and releases 2 electrons, and these 2 electrons are picked up by the copper, and the copper 2+ gets reduced to copper metal. So which one is the oxidizer? Which one is the oxidizer? Left or right? Which one is the oxidizer? The oxidizer gets what? The oxidizer is being reduced, isn't that right? So which one is the oxidizer? In this case? This one? Raise your hand. Or this one? Good, that's the oxidizer. Which one has the more positive potential? This one or this one? This one has the more positive potential? See, we're done. Review is done. I love that kind of review. Okay, so this... This was wishful thinking, because I really hate these reviews. Because I would like to tell you everything, but this would take 10 hours. And so I'm trying to make a selection, a totally random selection, which I think is something that is important to you, even if it's not in the final. I think it's important to you for your future exposure to chemistry. Okay, so now we have this where we have established that our red cat, this is the reduction, so we put this on the right side. So it's a copper metal into copper ions, and this is the oxidation. That's the anode, called the anode. Zinc metal here into zinc ion solution, same concentrations. There's one thing, you need to know what the Nernst equation is. I have not talked about this in lecture, but you need to know what the Nernst equation is. If you have different Oh, so that wasn't me. If you have different molarities here, for example, you have not one molar here and another molarity here, you need to be able to calculate that. That was in the homework, and this is not a very difficult problem. Okay, what is the Nernst equation? Epsilon 0 equals RT divided by NF, my log over ox over red, isn't it right? Yeah, all right, good. So you will know that. And this is nothing new, it was in the homework. I'm not teaching you something new here, all right? So this is how you do this. You need that salt bridge. Everybody needs to know why you need that salt bridge. I have explained this several times here in order to balance the charges here, because you have a change of charges. This will dissolve here, and this will become bigger because the copper goes out of solution here. That's where the reduction is. The copper gets reduced from copper 2+ to copper metal, and the zinc goes into solution, so eventually you will lose this electrode because all the zinc will be dissolved, and then you have no more galvanic cell. And you know, so that was the reduction is cathode. And you know that standard reduction potentials are listed from positive to negative potential. And they're all reduction potentials, okay? This is the reduction, the one above is the reduction. If you have 2 reactions, this one, for example, with this one goes in this direction, and this one goes in that direction, okay? So oxidizers oxidize all materials with lower potential. Oxidizers oxidize all materials with lower potential. That means they take off the electrons. This permanganate takes off the electrons of all of those here, okay? It even oxidizes gold. It oxidizes gold to gold 3+. See that? So the common denominator would be what? 3 times 5 would be 15, in order if you want to balance that equation, right? So again, I say it again, oxidizers become reduced, and reducers become oxidized in the process, all right? The standard reduction potentials are useful in balancing complex redox equations, redox reactions, and we have done that. Balancing redox reactions is here. You have MnO4 and bromine gives bromide. Bromide ion gives bromine and Mn2+. What's the oxidation state of the manganese here? What's the oxidation state or oxidation number of the manganese? What is it? Not you guys, up here somewhere. They go to my office hours. What is it? You said it, didn't you? 7, excellent, yeah? So oxygen is always -2. 4 times -2 is -8. But we show 1 to the outside. That is then -7. And so in order to balance this, manganese has to be +7. What's the manganese here, the oxidation state? Manganese is +2, okay? So how many electrons do we have to pick up here in order to go from 7 to 2? 5 electrons, okay? 5 electrons, that's obviously, it's a reduction. That's my reduction. That's obviously is my red cat here. And what bromide, what's the oxidation state of that? What's the oxidation state of that? Minus 1. And what's the oxidation state of that? 0. So that goes from minus 1 to 0. That's an oxidation. It's an increase in oxidation number or in redox number, or oxidation number. So that means you need at least 1 electron released here, okay? So now let's go into the table here. There it is right there. This is my first equation. This I write, and I have the potential is 1.49 volts for this. And then I need to find something with bromine. Bromine, Br2 plus 2 electrons gives 2 Br minus. Let's write this down. Br2 plus 2 electrons gives Br minus. So, but this is the reduction. We know that this is the reduction, and this is also a reduction, but this is not written right because that's supposed to be the oxidation, okay? So we multiply this with minus 1 and write this one here, and these two we write over here, all right? We can do that. You have to multiply the potential and reverse the potential if you want to do that. So, but now we have 5 electrons here and 2 electrons here, but if one oxidizes and the other gets reduced, they have to take up and give off the same number of electrons. So we have to have 10 electrons because the common lowest denominator is 10. 5, so multiply this by 2, and this you multiply by 5. So this gives 10 electrons. You multiply by 5, you have 10 electrons, and now we reverse it. Okay, so if I have this here, so I multiply the whole thing with 10 by 2 here, so I have 2 MnO4, let's see. I have 2 MnO4 plus 16 H3O plus how many? 10 electrons gives me 2 Mn2 plus I multiply by 2 plus 12 H2O. 12 times 2 is 24 H2O, okay? And then I have the bromide here. I multiply this by 5, 10 bromide, and 5 Br2 plus 10 electrons here. So I have 10 electrons here and 10 electrons here, so I can cancel those, okay? So what is the potential of this here? The potential of this is 0.149 volt, and the potential of this one here, this is now an oxidation, this is now an oxidation, but they are given as reduction potentials, is 1.06 volt. What is the potential of this one? What's the potential? The negative one. You can just reverse this. So if you put this over here, then it's negative 1.06 volt. So you have 1.49 volt minus 1.06 volt, okay? Or plus minus 1.06 volt. You add that potential, and with this you get 0.43 volts, okay? So you need to really know how to do that and how to balance an equation. Sometimes there's an exorbitant number, large number of electrons, which is your common denominator. Don't be intimidated if there are so many electrons, okay? Okay, so and this is, is delta G, is that positive or negative? When I have delta E is 0.43 volt, what would be delta G? Would this be a spontaneous reaction? Yes, because delta G is minus N is the number of electrons. Your number of electrons was in this case 10, remember? Was 10 electrons. That was the number of electrons. Was 10 times the Faraday constant times the change in potential, which is 0.43 volts, okay? And you always have to be careful if I, for example, give you delta G and want to know delta epsilon, the delta G, then you have to use joules, not kilojoules, okay? Be very careful. It's always in joules. There's no dimension of kilojoules, okay? It's joules. And let me see if you understand some of these things. And I have asked this many times, and now that's the last time. I think that's probably the last chem quiz we have. Of course, they don't count, but it's just for your own information. I said, which of the following will oxidize nickel but not silver? So is it Br2? Br2 is here. Nickel is here, and silver is here. So is it Br2, is it copper metal, or is it H3O plus? Which one will oxidize nickel but not silver? Well, you have 3 choices. Why don't you think about this? You discuss it with each other, please. I think it's the last chem quiz, ever, for me. Never say never, though. I might volunteer for this in a couple of years again. So tell your colleagues if they want to come next spring, it's not me. Okay? I say it here on YouTube. I'm not teaching Chem 1A anymore. Period. It was the last time. I love it, though. I hope you noticed. I teach a class where I have maximum 21 people. That's a different story, isn't it? I have more people in my office now. Okay, now let's come back to the serious business. There are quite a few people who have to study quite a bit still for the final. And I would go with C. I hope that I don't have to study also. I would go with C. So what happens? Which of the following will oxidize nickel but not silver? So silver is here. Silver is here. If it's above the silver, then it will also oxidize silver. So Br2 is above it, okay? So this will be reduced. It will pull these 2 electrons off the silver metal and make silver, put silver in solution, okay? It oxidizes silver. Okay, this one is out. Now let's say copper. Where's copper? There's our silver. Where's our copper? Copper is here, but copper is already in a form, so that would only go in this way. So copper is already in a reduced form, so that doesn't do anything. Now the last one we have is H3O plus. That's our hydrogen. H3O plus. And where's my silver? Silver would be, what is it? Nickel? Nickel has to be below because we want to go into this direction, okay? This is above, this goes this direction, and this goes this direction. That's not it, okay? That will not oxidize silver, it will reduce silver, okay? And this one is here, this goes in this direction, picks up 2 electrons, and these 2 electrons come from this reaction here. The nickel gets oxidized to nickel 2 plus 2 electrons. Okay, and the answer is nothing. There we go, all right? You need to know this. Stuff like this you need to know, right? So let's go back to lecture 2. We talked about the structure, and I'm not going to go through every lecture. I won't be able to, okay? Just a little bit of a quick race through the semester. We talked about the structure and the size of the nucleus and the atom. So the nucleus is about 10 to minus 15 meters, and the atom is itself about 10 to minus 10 meters. 5 orders of magnitude smaller than the nucleus, but all the mass is in the nucleus. We know how to obtain empirical formulas from experimental data. You use mass spectrometry. Mass spectrometry is where you ionize your sample, and then you have a positive charge. You accelerate this in a negative field, and you put it to a magnet, and the lighter it is, the more deflected it becomes in the magnet. And if you have a heavier one, it is less deflected, and you collect those then with certain masses, and you get a mass spectrum, and this is how these mass spectra look like here. You have your mass units, and let's see, what is mass 16? What is mass 16? Oxygen, okay? All right, what's mass 18? Oxygen 18 or water, right? Exactly. What's mass 32? Oh, it's right there. Okay, so CO2 is mass what? 44, okay? C12O16, CO2 is 44. That's the one we're using usually. All right, so this is mass spectrometry. And then we talked about radiation. Radiation and light. So light we know that light can be photons, but it also can behave as a wave. So there's a particle and a wave, and we have shown that light has an interference pattern, okay? Because it behaves as a wave. Only waves have an interference pattern, okay? The waves how can waves interfere with each other? There are two ways to interfere with each other. The one is constructive and the other one destructive. When it's constructive and you have light, would it be the same intensity than the initial light, or would it be a stronger intensity, or would there be no intensity? Stronger intensity, actually. This is here, that's how we plot the intensity. That's the strongest, and it gets weaker and weaker and weaker. And here are dark spots. There's no light, okay? There's a dark spot because there's destructive interference. Okay, and so we talked then about that light can behave also as a particle. We established it's a wave and a particle, and then we have, how are we going to go about to unify this? We say, the one guy said, hey, you guys over here say, it's a wave, and I say, no, it's a particle, okay? And so we rectify this, that the wave has a wavelength, okay? The wavelength is lambda, and the particle has momentum. Momentum is mass times velocity, and so this is what would signify the wave, and this is the particle, and with this you have here this Planck's constant. Lambda is the wavelength, is Planck's constant, times p is the momentum, okay? So if you have a wavelength, you can assign a momentum to it. If you have a particle, you have a momentum, you can assign a wavelength to it. This is the de Broglie relationship, and there's this duality between those. Now, in lecture 5, can you imagine I have to go to 30 or something? It's lecture 5. We know that electrons, not only light, but electrons, we know they are particles, okay? They have a mass and they have a velocity. Anything that has a mass and a velocity is a particle, okay? But they also can behave as waves. They show interference pattern, and we have talked about this really in great details. And also there you can use Mr. de Broglie's relationship to again unify the particle and wave character of electrons. And this was the fundamental understanding of orbitals then, because they travel as waves, as standing waves. And this is why we went through all this, that you understood that what you know is a mass particle, that it behaves as a wave around the atom. The electrons behave as waves around the atom, and they behave like standing waves, and the energy is quantized. What is the lowest energy level? N equals 1, not 0, okay? It still has energy, potential energy, okay? And the magnitude of the de Broglie wavelength tells us if you're dealing with a quantum particle. Let's see, this is our standing waves here. You have N equals 1 here, you have half a wavelength in this case. So then you have N equals 2, you have a full wavelength. That would be, if this would be the increasing energy, it would be a level 2 then. And you have one node here, you see that? And then would be 1.5 wavelengths. How many nodes do you have? That would be higher in energy because you have, so you go from N equals 1 is the lowest possible energy, higher energy, higher energy, higher energy, higher energy this electron can have, all right? And so the number of nodes is 3, the number of nodes is 2, 1, 2 here. The node is always where the wave function goes through 0. It's not 0, but it goes through 0, all right? And so then we talked about these quantum particles have both a wavelength and a momentum, okay? But if you have non-quantum particles like a truck or people, doesn't matter how tall they are, okay? People, then you are not a quantum particle. This is not a quantum particle. You can calculate a wavelength. The wavelength has always to be sort of in the size of the object, around the size of the object, okay? And if you have a wavelength of a baseball, 6 times 10 to the minus 26 nanometers, so this is 6 times 10 to the minus 35 meters. It makes no sense. There's not the universe, you can't even divide it small, actually, okay? And so that makes no sense. That is not, a baseball is not a quantum particle, all right? And a truck neither. So in lecture 10, so I jumped 5 lectures, we talked about electronic configurations. We had this Aufbau principle, the build-up principles, where we go from the lowest orbital, the 1s, 1s1, 1s2, 2s1, 2s2, 2p1, 2p3, 2p2, 2p3, 2p4, 2p5, 2p6, and so then we come to the 3, and so on and so on. And so you know what the rules are. What is the next one? M sub L, M sub S. These are the 4 quantum numbers, how you build up orbitals. And so the Hund's rule is when you're filling degenerate orbitals of the same energy, the electrons fill them singly first. Remember, they're sitting in the bus, and everybody sits first by itself on the seat, and then you fill up when the level is filled with half-filled orbitals, then you fill them with the second orbital. What's the difference between the two? What's the only difference between the two? If you have 2 orbitals in the same, 2 electrons in the same orbital? The what? The spin is different, okay? One is up, one is down, okay? Plus 1/2 and minus 1/2. So we've seen this here, you know how to do this also. You can also see if it's magnetic. If it has unpaired electrons, then it's magnetic. The more unpaired electrons you have, the higher the magnetism, all right? So if you now start pairing here in fluorine, for example, the P5, P6, you are done, and then you fill the 3s. And so, you know, there's s orbitals, p orbitals. What's the next one? How many d orbitals are there? How many d orbitals are there? 5, exactly. How many electrons are in the d orbitals altogether? 10. What's the next higher level? F. How many f orbitals are there? How many electrons are in there? 20. Very good, excellent, okay. So there are orbital blocks in the periodic system. We have seen that's the 1, 2, and so on. This is the s block, and that's the p block, that's the d block. These are the f blocks down here, okay? And homolog elements in the periodic group exhibit often similar chemical behavior. So lithium and sodium, or silicon and germanium, or sulfur and selenium, or chlorine and bromine, they have similar behavior. Why is that? They have the same number, identical number of valence electrons, the outer electrons, but they're in different energy levels in higher orbital, okay? And so then we talked about ionization. Let me go here. Ionization is, what is ionization? Is when you have an electron is taken off an atom. You leave behind a positive charge, and because the electron is negative, so this is an ion.